I do not like this problem, and I'm going to show you why. The first part is not bad. So, uh, the first thing we want to prove is the first thing, and so let A and B be in. We're going to call this group G. Then AB is in G. So AB squared equals 1, i.e. ab equals 1. And so let's see, if we multiply both things on the right by B inverse, and then by A inverse, we'll end up with AB equals B inverse A inverse. But since A squared equals 1, A inverse is A. So same for B, so this is BA. Hence, G is abelian. Okay, so that's that. That's not bad. So now if A cubed equals 1 for all A in G, then G may or may not be abelian. And this is why I don't think this is a fair problem. First of all, you can come up with a very easy example of an abelian group in which A cubed equals 1 for every A. Just consider the group that's just 1, A, and A squared, where A cubed equals 1. It's easy to see that this is a group, and then what happens if you cube every element? 1 cubed is 1, A cubed is 1 by definition, then A squared cubed is just A squared cubed is A to the 6, which is equal to A cubed squared, which is just 1 squared equals 1. And so this is a group, and every element cubed is 1. And the other thing, like, because multiplication of integers is commutative, then the exponents are commutative, and so this group is commutative. So that's that. But so from that, you know that if you want to prove, like, you can't just take it's not the case that every group of this let's call it a cubic group. I don't know. It's hard to call things because a lot of the good names are taken up by things. So if I say, oh, let's call it a cubic group, there's probably something out there called a cubic group, and there's going to be conflicts with them. So, okay. So let H be a group such that for all A and H, A cubed equals 1. Okay, so now we know that H need not be non-abelian. It could be that H is abelian. So we either need to prove that H is always abelian necessarily from this property, or we would need to come up with an example of a group H which is not commutative. And that's what you have to do for this problem. You have to find an example of a group such that A cubed equals 1 for all of its elements, but which is not abelian. And the simplest thing I could find, I looked into this a little bit, the simplest group I could find is called the, let's see here, Heisenberg group mod 3. I mean, it could be that there's a simpler group of this type, which is not abelian. Well, actually, let's take 1A squared, 1B squared. No, but then, like, you have to consider what happens when you multiply A and B together and stuff. That this is going to be a really difficult problem, and it seems like way beyond the other stuff that comes into this, that we've covered in this course, or we've covered in the problem so far. So it turns out there's something called the Heisenberg group mod 3, and it's like a group, and you've got like, it's generated by 1 B C, and A cubed and B cubed and C cubed are all 1, and you've got a whole bunch of other relations that define it. And so what you would have to do with this problem is you'd have to say, okay, well, first of all, you'd have to have some way to come up with this group, unless you just said, hey, I looked in a textbook and I found this group, and now I'm going to prove that it works. If you had no idea that the Heisenberg group mod 3 existed, what you'd have to do is you'd have to like start going through like, okay, so let's take 1a squared, 1b b squared, and then throw everything in here that might not be of this form. Like you'd have to include ab and a squared b and ab squared, and then the same things for b and a flipped. Then you have to show that everything's a group, and it just wouldn't, I don't know how you'd go about doing this nicely. And then if this didn't work, you'd have to go on 1c squared, and then eventually there, like, you'd end up with the Heisenberg group, but I don't know how you would get to that point nicely. Anyway, so you've got this thing, so this Heisenberg group mod 3, it's got a bunch of relations on it, and you'd have to prove that this set combined with these relations does indeed form a group, which I think you can do, but we don't really have the techniques for that yet. Like, there's a section in this book on groups and relations, but I think it's a little more down the road. But not only that, but you'd also have to show that it's non-commutative after doing that. I don't know how you'd come up with this in the first place. So I really, just because of how much more difficult it is to, like, it's significantly more difficult to find a non-abelian group such that a cubed equals 1 for every a. It's so much more difficult than proving that, this first part, that I don't think it's really a fair question to put in a problem. Although the way he phrases it, like, it's like, what if a cubed equals 1 for every a? Maybe the point is to just kind of show you this phenomenon, and this is a phenomenon that happens a lot, especially in algebra, where you're dealing with like discrete things, where you look at a statement that has like a number in it, like 2, and you want to prove something involving this number, and you go about it and you find out, oh, hey, this is actually pretty easy, this really isn't that bad. And then you'd be like, okay, well, what if we extend this by 1? What if we make it 3? And then it becomes significantly more difficult. And there's tons of examples of this. For example, if you're trying to do anything like analysis related, and like you do something in the real line, and then you say, oh, well, what happens if we move up to dimension 2? And then everything just kind of gets way more complicated. And there's plenty of more examples like this, where even in partial differential equations, like you want some partial differential equations that describe water, and how do you solve them? If you're in dimension 2, then the equations are pretty simple, and Euler solved them back in like the 1700s or whatever. And then you say, oh, well, we don't live in 2D, we live in 3D, so let's extend this to 3D and ask the same question and try to solve this equation that describes water. And this, of course, is a Navier-Stokes equation, which it sounds like we really have no clue how to say anything really meaningful about this. At least I've heard mathematicians say things along these lines. And of course, it's one of the millennial problems, and so there's $1 million reward if you can solve it, and it's been open for like hundreds of years, and we're still way far behind, and that's just going from dimension 2 to dimension 3. So this is just an example of that, where like, oh, a squared equals 1, oh, that's easy. A cubed equals 1, oh, you have to go up to groups of order 27. And so it just seems a little bit too difficult for where we're at in this course. But anyway, that's my 2 cents on it. I mean, I don't know. Maybe I'm just being stupid, and there is a really simple solution out there that's similar in simplicity to the first part, and I'm not seeing it. But I wasn't able to find any simple simple examples of groups. Not examples of simple groups, because that's a like I'm saying with this things. Like you have to be careful what you call things, because simple is already used a lot, and also regular and normal, those words get used a lot, but there's no examples of very easy groups that are such that a cubed equals 1 for every a, and which are non-abelian. So basically, there you go. This is what I have for a solution. I don't know if you can consider it a full solution, but given where we're at, I think this suffices.